SU2 is spin.
Yeah. That's also spin. But the P operator is the momentum operator.
It's a pattern.
But the momentum operator carries all the information about the spin.
Okay, the topic of my talk is on the thermodynamic stability of the variable Chaplygin gas.
Not in the key doctor.
We know that our present universe is accelerating. There are some plausible explanation. First explanation, cosmological constant. But it is the simplest candidate to explain the accelerating universe. However, it suffers from a fine-tuning problem if it originates from vacuum energy. There is another type of explanation is called dynamical dark energy model. We classify the model into two classes. We have used another one, the cosmological constant. But using Einstein's equation, we cannot explain the accelerating universe. So we want to modify this equation. First of all, we can modify left-hand side or modify right-hand side. There are several explanations to modifying gravity, say FR gravity, scalar tensor theory, brane walls, higher dimensional space-time, etc. There is another explanation to modified matter, right-hand side, quintessence, K-essence, Chaplygin gas, inhomogeneity, etc. I want to talk restricted on only Chaplygin gas model. This is the simple metric, FRW metric. The equation of state of the Chaplygin gas is P equal to minus B by rho, where B greater than 0, a positive constant. P is the pressure and rho is the energy density of the fluid. Now from energy conservation principle, we can give this equation rho dot plus 3A dot by A into rho plus P equal to 0, where A is the scale factor depending upon time only. From this equation, we can get the expression of rho, where C is the integration of constant. If we see the equation of rho, when A is small, the rho tends to infinity and P goes to 0. That is dust dominated universe. If A is weak, then P equal to root over B and rho equal to root over B and P equal to minus root over B, which gives the equation is previous page. So I told this past, when A small, rho large, P tends to 0, that is dust dominated universe, and present A large, rho small, P less than 0, negative, P equal to root over B and rho equal to root over B and P equal to minus root over B. This is a lambda CDM model. Actually, this model corresponds to unified dark energy model, but this model does not fit data well unless one modifies and generalizes it with extra parameters. There are several kinds of modifications, such as the introduction of alpha with the power in the power of rho, that is the equation of state P equal to minus B by rho to the power alpha, where alpha greater than 0. From this equation we can get the effective equation of state. Effective equation of state means P by rho, that is omega tends to 0, that is dust dominated universe, but present universe omega tends to minus 1. Observations seem to favor the generalized Chaplygin gas over other models. There is another kind of generalization known as variable Chaplygin gas. Professor Zhang and Guo Actually, the original Chaplygin gas was P equal to minus B by rho, introducing that the P is a function of scale factor A, and they take B equal to B0 a to the power n, where B0 and n are constants. When we put n equal to 0, we go to the the equation reduces to the original Chaplygin gas. This value, the value of n may be positive or negative, but from the observational data, they showed that the value of n equal to minus 3.4. Later, another article, they showed from observational data, the base fit value of n equal to minus 3.0. This results that when n less than 0, n negative, this results favors a phantom-like Chaplygin gas model, which allows for the possibility of dark energy density increases with time. Relevant to mention that recently there are some indications that a strongly negative equation of state omega less equal to 1 may give a good fit with observations. There are some references. But in another work, same variable Chaplygin gas, Gitanjali, Sethi, etc. et al., they have shown the value of n lies between the interval minus 1.3 to 2.6 from these observational data. Now, my motivation. We have seen that the several type of value of n, the value of n may be positive, negative, or 0 from observational data. So, to explain the observational data on accelerating universe, workers assumed various type of gas models obeying different equation of state. However, it is not enough to just feed the data only. One should also check if the gas models are realistic, that is thermodynamically viable. They should satisfy the stability criteria, especially del P del V for constant entropy less than 0 and CV greater than 0. With this motivation, we have studied the stability criteria of this recent work of Go et al. Previously, Santos et al. Have studied the thermodynamical stability in generalized Chaplygin gas model. Generalized Chaplygin gas model means equation of state P equal to minus B by rho to the power alpha. But our work is on varying Chaplygin gas, where P equal to minus B function of A, that is B0 e to the power n by rho. Yes. We investigate the thermodynamical behavior of the variable Chaplygin gas and to see if it is thermodynamically stable. Now, formalism. We have taken B equal to B0 V to the power minus n by 3 because scale factor is A cube equal to B. From this, therefore, B equal to B0 V to the power minus n by 3. We know that rho equal to U by V, where U is the internal energy and V is the volume. From general thermodynamics, we know that del U del V is equal to minus B. Using the previous equations 1, 2 and 3, we get equation 4. The expression of del U del V is equal to B0 V to the power minus n by 3 V to the power alpha V to the power alpha minus A U by V. The integrating equation 4, we get the expression of U. Here C is a integration constant which may be a universal constant or a function of entropy S only. Now we have taken C is a function of S and B0 also function of S. The term capital M for simplification equal to 6 minus n by 3 and epsilon equal to nc by 2 B0 whole to the power 1 by n, which have the dimension of volume. Next, from the above equation, we get the expression of rho of the VCG model. Now we have studied the thermodynamical behavior. First, pressure. So using the previous equations, we get the expression of pressure. Here, if look equation 7, right hand side, when d is small, that is passed, p goes to 0, and when v tends to infinity, p negative. From figure 1, we have seen that I use two values of n. First of all, n equal to 0 and n equal to minus 3.4. Both the graph starts from 0 and v at v equal to 0, and v increases. Both the graph goes more and more negative. This figure shows that p goes more and more negative with v, implying a continuous transfer of energy from dark matter component to dark energy. When n equal to 0, the above results reduces to Chaplygin gas model, pure Chaplygin gas model, and its thermodynamical behavior was discussed earlier by Santos et al. For n less equal to 0, the pressure goes more and more negative with volume. Actually, cosmic late time acceleration implies that there exists a continuous transfer of transfer of energy from the dark matter component to dark energy 1. Now we get p equal to 0 at v equal to 0 at any value of n. We have shown previously from the graph also. It also follows from the above figure that I have written here. N becomes more and more negative, the pressure falls sharply. Now we have studied equation of state. Using the previous equation 6 and 7, we get the equation of state W equal to P by rho. From this figure, when n equal to 0, acquiescence phenomena shown, and when n less than 0, we see the phantom-like phenomena. For small volume, V less equal to epsilon, that is epsilon V much greater than 1, that is W tends to 0, therefore P equal to 0, we get dust dominated universe from the equation of state, and it is independent of n. Another, when large volume D is mass less than 1, the equation was previous page, sorry. From this equation, equation 8. Large volume V is mass greater than epsilon, that is epsilon by V is mass less than 1. At that time, W is nearly equal to minus 1 plus n by 6. Now from equation 9, we see that if n less than 6, W is always greater than minus 1. So this is not lambda CDM, but when we put n equal to 0, this will be lambda CDM. Here influence of n is prominent. From equation 9, it follows that for positive values of n, the value of W will be between 0 to minus 1. So we get a quiescence phenomena and big reef is avoided. However, in what follows, we shall presently see that to preserve the thermodynamic stability of VCG, n should be negative. Latter part I have shown. For n less than 0, we get W less than minus 1, the phantom-like model. It is seen from the figure 2 that W is more negative for n equal to minus 3.4. Here n equal to 0, below this n equal to minus 3.4, it was more negative than n equal to 0 value. I have previously studied modified Chaplygin gas in higher dimensional space-time and showed that in the presence of extra dimension, the model became phantom-like, but when extra dimension is absent, our results seem to be lambda CDM. Only one may see that the experimental results favor like VCG model. Now we have studied deceleration parameter. Now Q equal to minus A dot dot by A dot square. From our equations we give the expression of Q, and graph is shown here. When V Q versus V graph, when V is small, we have 0. We have seen that with the value of Q is 0.5, that is positive. That means at V at is 0 means dust dominated universe. At that time Q equal to 0.5 means positive, that is we get decelerating universe. And after that when V increases and flip occurs, accelerating flip occurs, and V more increases and we get Q the value of Q negative, more and more negative, and we get accelerating universe. But early flip is shown for n equal to 0. Here is the analysis. For small volume, when V is much less than epsilon, that is epsilon by V is much greater than 1, which gives Q equal to half. That is Q is positive, universe decelerate for small V. There is no effect of n on Q at that time, early V. But for large volume, V is much less than epsilon, that is epsilon V much less than 1, which gives Q equal to minus 1 plus n by 4. From figure 3 it follows that as volume increases, Q goes to 0 first and then universe accelerates. From accelerating flip to occur, the flip volume say Vf is in the following form: Vf equal to minus epsilon 2 by 4 minus n whole to the power 1 by n. We give from equation 11, which shows that the Vf to have real value n must be less than 4, otherwise there will be no flip. This is in accord with the findings of the experimental results, Guo and Zhang. Our main purpose to check stability. We know to check the stability, thermodynamic stability condition, to determine first del P del V less than 0, and also thermal capacity at constant volume CV greater than 0. From 1 and 7 we calculate del P del V at constant entropy here from at equation 12. In an earlier work, Sethi et al. Showed that the range of n lie in the interval minus 1.3 to 2.6 from some observations, and another observation they showed minus 0.2 to 2.8. But from equation 12 we see that n less equal to 0, for n less equal to 0, del P del V less than 0 throughout the evolution. From figure 4 gives the similar type of conclusion. For n we have taken n equal to 0 and n equal to minus 3.4. Positive value of n is not, so we can say positive value of n is not compatible in VCG model. It may be concluded that to get thermodynamical stable evolution, the positive value of n should be discarded. Now, verification of CV greater than 0. We know that the expression of CV equal to T del S del T at constant volume. So first we have to calculate T and S. From equation 5 we get T equal to del U del S V. At equation 30. Here we have seen that dB0 by ds and dC by ds, because I told previously that B0 and C may be universal constant or either universal constant or function of entropy. Now we have using the function of entropy, so dV0 by ds plus dc by ds. But if we put that B0 and C is a universal constant, though, so right hand side will be 0. If C and B0 are also assumed to be universal constant, then dc by ds equal to 0 and dV0 by ds equal to 0. The fluid in such condition remains at 0 temperature for any value of its volume and pressure. Therefore, to extensively the thermodynamic stability of the variable Chaplygin gas, whose temperature varies during its expansion, it is necessary to assume that the derivatives in equation 13 are not simultaneously 0. So, empirically, we have no direct knowledge of what this function should be. Theoretically, however, we know that this function must be such as to give positive temperature and cooling along an adiabatic expansion, and we choose that del C del S greater than 0. Now, using from equation 5, dimensional analysis, we observe that the dimension of C to the power half equal to dimension of U, which implies C to the power dimension of C to the power half equal to dimension of U equal to dimension of T into S. From this, we can write C equal to 1 by beta square S square, where beta inverse is a universal constant with dimension of inverse of temperature, say tau, beta inverse equal to tau. Now differentiating equation 14, equation 14, differentiating dc ds equal to 2 tau square s. In order to have positive temperatures and cooling along an adiabatic expansion, we must impose now dV0 by ds equal to 0. Therefore, the expression of T, temperature, will be in equation 16. Now from little calculation and straightforward calculation, we get the expression of entropy S equal to this. Now from equation 17, for positive and finite entropy, capital T must be between 0 and tau. Evidently there is another, at capital T, that is temperature equal to 0, we see that S equal to 0, implying that the third law of thermodynamics is satisfied. Now the thermal capacity at constant volume can be written as Cv equal to T del S del Tv equal to this expression. Since 0 temperature capital T lies between 0 to tau, so from equation 8 we have seen that Cv is always greater than 0 irrespective of the value of n. Now I have studied the thermal equation of state. Since P equal to function of temperature and volume, using previous equations 5, 14 and 17, we get the expression of internal energy both V and T. U equal to 2B0 by n whole to the power half V to the power n by 2 into 1 minus T square by tau square whole to the power minus half. Now with the help of equation 1, 2 and 19, the pressure will be P equal to this, which is also a function of both V and T. For T equal to tau, we have seen that P equal to 0, the universe behaves like a dust-like or a pressureless universe. Unlike the work of Santos et al., we do not get de Sitter-like universe due to the presence of the term V to the power minus n by 6 in equation 20 for the case of T tends to 0. Actually, for Santos et al., they shown that at t equal to tau, they get de Sitter-like universe, but we do not get due to the presence of V. Now using equation 2 and 19, we further get the expression of rho. Again, we can get the similar expression of rho using 1 and 20. We have using 2 and 19. Similar expression can of rho with the help of equation 1 and 20. Now using 20 and 21, the thermal equation of state parameter P by rho omega equal to minus 1 plus n by 6 into 1 minus t square by tau square. The thermal equation of state parameter is an explicit function of temperature only, and it is also depends on n. As volume increases, temperature falls during adiabatic expansions. In our case, for t tends to 0, the equation 22 yields omega equal to minus 1 plus n by 6, which is identical with the equation of 9 previously I have shown, as it is in the case of large volume. Again, when t tends to tau, omega tends to 0, which is indicating dust-dominated universe. Now we have to examine the well-known thermodynamical relation del U del Vt equal to T del P del Tv minus P. Using equations 19, 20, we find the relation is also satisfied. This equation also satisfied using equations 19, 20, and 19 and 20. That means first and second law of thermodynamics are also verified, because equation 23 comes from first law and second law of thermodynamics, this relation. Now concluding remarks. We have considered n equal to minus 3. The pressure goes more and more negative as volume increases. Actually, cosmic lag time acceleration implies that there exists a continuous transfer of energy from dark matter component to dark energy one. Second, the effective equation of state is shown in the equation 8. At large volume, we have seen that for n equal to 0 gives lambda CDM model. Influence of n is prominent for sufficiently large volume. For n less than 0, W less than 0 leads to phantom-like cosmology, which is in favor of the current supernova on a constant like VCG model. The above phenomena is shown in the figure 2. I have discussed third, the deceleration parameter is studied in the context of thermodynamics, as is shown in figure 3. Our analysis shows that for the acceleration flip to occur, the value of n less than 4. This is in accord with the findings of the current observational results. 4. The most important area of our concern in the question of the thermodynamic stability of the gas chosen. Firstly, we have to determine whether del P del V is less than 0. The analysis shows that for n less than 0, del P del V is less than 0. So one important conclusion done here using equation 12 is that the value of n must be negative. Interestingly, this result is in agreement with the observational results found earlier by Go et al. Due to this reason, we have taken n equal to minus 3.4 to study the whole work in this article. In this context, the thermal capacity at constant volume Cv is also determined, and it is seen that Cv is also positive irrespective of the value of n. So both the conditions of thermodynamic stability of the fluid are studied, which shows that the fluid is thermodynamically stable throughout the evolution process only when n is negative. Fifth, the expression of entropy is derived and shown in equations 17. In this equation, it is seen that T equal to 0, S equal to 0 implying that the third law of thermodynamics is satisfied. Since the thermal equation of state is discussed in this work, where it is seen that the volume is not explicitly present in the expression 22, this thermal equation of state parameter is an explicit function of temperature only. As volume increases, temperature falls during adiabatic expansions. In this case, for T tends to 0, equation 22 yields W equal to -1 plus N by C, which is identical with the equation of 9, as it is the case of large volume. Again, as T tends to tau, omega tends to 0, pointing to a dust-dominated universe. Finally, we have examined the well-known thermodynamical relation, which comes from the first and second law of thermodynamics. That means first two laws of thermodynamics are also verified.
Anyway, thank you very much for this presentation. I was wondering, it's my understanding that if you look at the expansion of the universe, then you get a general relationship between energy that condenses in the Big Bang star. If that is something to believe in, then it's all energy and it condenses into matter. And the first or second summary suggested that matter is transferred into energy. And I just wondered, is there a conflict with our concept of initial expansion, or is this interpreted in some other way?
Actually,
Dark matter component, dark energy, I understand the star, but it's still matter to energy. And I just wondered how that fits into our concept of energy expanding and matter condensing out of it.
actually, to explain the accelerating universe, there are some kind of repulsive force acting, we don't know, that is called to explain this, we have taken a concept of dark energy. So as universe accelerate more and more dark energy formed. Now presently 70% I think dark energy. The dark matter is about 25% and baryonic matter is 5%.
In my research into this area, I find that there are some logical inconsistencies with the dark energy and dark matter interpretation to try and preserve general relativity theory. And the data from the outer arms of spiral galaxies plus the Pioneer 10 and 11 spacecraft data with the anomalous acceleration are logically inconsistent with dark matter being a quantity of nature. I just throw that out. To what extent does your work depend on the interpretation of dark energy and dark matter?
Actually, interpretation, I have only checked the thermodynamical behavior. I have seen that the several papers, there are so many data and so many possibilities. Say here, for varying Chaplygin gas, I have seen the values of N may be positive or negative. So I have studied only it is possible, which value is N is possible. So I have only studied the thermodynamical behavior, that which value is possible for N.
So you're saying your study of the universe in terms of the thermodynamic
there should be
is independent of the interpretation of dark matter and dark energy, but it's consistent with it.
consistent with some observational data. Some those who are observations. I am not working with observation. They should actually. I don't know what will be the actual explanation. Future will tell what will be the actual explanation. I have given an equation of state having Chaplygin gas. They gave the explanation here. So I told this. But I have only studied the thermodynamical behavior because I have seen that there are several values of n, which values of n is actually possible, which is thermodynamically actually compatible.
Comment and a question. In the cosmology that I use, a multiverse cosmology has some association with Ludwig's. The rest of the multiverse, that's where dark energy is. The force of that dark energy is what balances the cosmological constant, so it becomes a much simpler issue. A couple of months ago when you applied to the conference, I had never heard of a Chaplygin gas, so I Googled it, but now I've forgotten. Can you give a generic definition of a Chaplygin gas?
Chaplygin gas?
Yeah, just a little generic definition.
Generic definition?
Yeah, define in the simple terms what you mean by a Chaplygin gas. It's not just, it's a cosmic gas, or it has
No,
certain
it's actually,
properties?
this is in, I think 1900 or 1900 for fluid mechanics, Chaplygin using this equation of state P equals.
So it's more than one type of chemical structure. It can have different chemical structures. And it's of interest because it has some thermodynamic variability that makes it interesting to these kind of observations. Is that the case? I've forgotten exactly what a Chaplygin gas is.
E equal to minus B by rho. This equation is the equation of state is the P Chaplygin gas.
So any
Different equation of state, right?
This equation of state used by Chaplygin and fluid mechanics.
but are there some specific gases that you use as Chaplygin? Or am I missing the whole point of your? I understand the part of your presentation, but I don't. It's not clear to me what a Chaplygin gas is.
Isn't it just a different equation of state?
That's all.
You
But
start with it, to get a Chaplygin gas has a different equation of state from the,
But there are gases in physical reality that are these particular gases are Chaplygin
I don't know.
gases, or is it
That I
not?
don't know.
That's what I'm asking.
I
What-
know
is
there's a
there
whole
specific
infinite choice of equations
example of a
of state.
Chaplygin gas?
Specific type.
What is one? What is a Chap? Is there a
why
specific
is it special?
chemical?
His question is, why is a Chaplygin gas special for you?
Or is there a species of a chemical species that is a Chaplygin gas, or is it something?
No.
Yeah.
Wikipedia. Chaplygin gas, which occurs in certain theories of cosmology, is a hypothetical substance that satisfies an exotic equation of state if one rho is equal to negative A over rho to the alpha.
All right, that's what I was looking for. Thank you.
They're basically quintessence.
All right.
Is what they call quintessence.
Yeah, that's about the farthest thing out in cosmology. It's about lunchtime. Lunch is one floor below us. I was just down there a minute ago. They hadn't come yet, but hopefully they will be. Yeah, it's an hour. We have an hour, so come back in about an hour.